For f of x equals the ln of x divided by the square root of x, find the intervals on which f is increasing and decreasing, find the local maximums and minimums, use concavity and inflection points to sketch the graph. So we are going to look at all those things. It's probably also helpful to look at domain, symmetry, zeros, intercepts, all that good stuff, but I'm going to just focus on the first and second derivative information and how that helps us to sketch the graph. So just quick note, the domain is x has to be positive in this problem. So let's take a look at f prime of x. F prime of x using quotient rule is 1 over x times x to the 1/2 minus 1/2 x to the negative 1/2 times the ln of x all over x to the 1/2 squared, which is x to the first power. So we want to factor out anything we can from the numerator in order to get our critical values by setting the numerator to 0 and the denominator to 0. That is, we want to know when we have horizontal tangent lines when the numerator of the derivative is 0, or when we have undefined tangent lines, that is, when the denominator is 0. We can simplify these two together to get an x to the negative 1/2 power there, and that will give me an x to the negative 1/2 and an x to the negative 1/2. So I'm going to factor out an x to the negative 1/2 out of the numerator, leaving me with 1 minus 1/2 the ln of x over x. Now I'm going to bring that x to the negative 1/2 to the denominator and combine it with the x that's in the denominator already. Since I don't really like fractions, I'm going to factor out a 1/2, making this factor out the 1/2, giving me 2 minus the ln of x over x to the 3/2 power, or what I would prefer is 2 minus the ln of x divided by 2 times x to the 3/2. I think that's the most compact form that we can get this problem into. So we want to know when we have the derivative equals 0. So that means the top equals 0 when 2 minus the ln of x is equal to 0, or when the ln of x is equal to 2, or when x is equal to e squared. On the other hand, we have when the denominator is equal to 0, when the bottom equals 0, that is when 2x to the 3/2 is 0, or when x is 0. This is already not part of the domain of the problem, so that is an endpoint of the domain. So I'm going to use a number line to determine the intervals on which this function is increasing or decreasing. Here you have 0 and nothing is happening to the left because it's outside of the domain of the problem. Here we have e squared. All I care is whether or not the function is, the derivative is positive or negative, and that tells me about the slope. That tells me about the shape of the f of x. I'm going to pick a value here in between 0 and e to the second. How about e to the first? Using e to the first on the most simplified form, that is this form here, I will see that the ln of e to the first is 1. 2 minus 1 is a positive number. And then when we put e to the first in for x in the denominator, we also have a positive number. So the function is increasing from 0 to e squared. Let's pick another value to the right. How about e? I like powers of e because they work well with ln's. So if I evaluate this at e to the third, I have 2 minus the ln of e to the third is just 3. So 2 minus 3 is negative on the top. And on the bottom, e cubed is a positive number. When you cube it, it's still positive. If you take the square root, it's still positive. If you multiply it by 2, it is still positive. So we see that the function is decreasing from e squared to infinity. That tells us that there is a local min when x is e squared. That is, we will have a local, what did I say? Not min, max. Max, we will have a maximum value of y when x is e squared, because this function is increasing, then decreasing. This will also be an absolute max, since if the function is only increasing then decreasing, it doesn't have a chance to have a y value that's greater than whatever this y value would be. So you could point out that it is also an absolute max. Now we want our second derivative and our second derivative information. So I'm going to use the quotient rule and take the second derivative, derivative of the top times the bottom, minus the derivative of the bottom times the top, all over the bottom squared. Again, we are looking for any values of x that will make this fraction 0 or undefined. And we should expect to get our endpoint of our domain here as one of our values. And you see the denominator. If x is 0, this would make this fraction undefined. So that's going to be in there. All right, let's simplify what we can. I see a 2 and a 2, like that. I see x to the first and x to the 3 halves. So I'm going to cancel one of these with one of these to get an x to the 1 half. Now I notice that there's an x to the 1 half common to those two terms. There's also a negative common to those two. So I'm going to factor out a negative x to the 1 half power. What do we have left up top? Looks like we have a 2. Then we have a plus 3 times 2 minus the ln of x. And on the bottom, we have squaring this 4x to the third. Also, since this is multiplication right here, I can simplify the x to the half and the x to the third, and I get 2 thirds is 6 halves, and that would give me a result of 5 halves there as the exponent. So we have negative brackets 2. There's a plus 6 minus 3 ln x, and then at the bottom 4x to the 5 halves. Okay, so then this is equal to negative 8 minus 3 ln x over 4x to the 5 halves. What makes the top 0? Top equals 0 when that negative won't matter here to make the top 0 is the same as this. Skipping some steps. Raising to the powers here. Changing from log to exponential form. Okay, so x equals e to the 8 thirds, and of course, you're looking at the denominator, x equals 0. So I'm going to use this second derivative and make my number line, which will tell me about the concavity. Here is 0. Nothing is happening over here. That's outside of the domain. Here we have e to the 8/3 power. And we're going to pick a test value inside of here. I'm thinking e to the 1st power again. So if I use e to the 1st power, I have that negative out front. 8 minus 3e to the ln of e to the 1st. That is just 8 minus 3. 8 minus 3 is positive. And then on the bottom, we have e to the 1st raised, well, e to the 1st is a positive number. If you raise it to the 5/2 power, it's still positive. Times 4, it's still positive. So this is negative. So we're looking at concave down. And over here, if I use e to the, I need something bigger than e to the 8/3. How about e to the 9/3? That would be okay. E to the 9/3, or that would be e to the 3, right? So the ln of e to the 3 is 3. 3 times 3 is 9. So we have a negative out front. We have 8 minus 9 is a negative. And on the bottom, we have a positive. A negative times a negative is a positive, divided by a positive is a positive. So over here, we've got concave down. Over here, we have concave up. Looks like somebody's not happy and somebody is happy here. And that means at e to the 8/3, we have a point of inflection. So to put this together with the previous graph, we have something like this. We've got e squared. We have a little bit further to the right is e to the 8/3. I didn't bother getting y values in this problem just because I don't care. You would probably want to type these things into your calculator to get some y values. I am going to get one y value. I'm going to get the x-intercept. Notice when x equals 1, we have an x-intercept because the ln of 1 is 0. So here we have e squared is 2 point something squared, so that's bigger than 1. So here's 1. So the situation we have is a function that is increasing, has an intercept at 1, hits a maximum at e squared. It's concave down until it hits, I'm going to move this over to make my graph look nice, until it hits e to the, what was it, 8/3, and hits a point of inflection, whatever that is, and then it curves like so. To find some more features of this, we can look at the limit as x approaches 0 from the right. That would show us the behavior over here. And to show us the behavior over here, we could look at the limit as x approaches infinity. Both of those, well, this second limit you can use L'Hopital's rule to find, and the first limit you could notice that the top is getting very large and the bottom is getting very small, and so a negative very large number divided by a positive very small number is still a very large number to see that you've got that vertical asymptote. And that is a graphing problem. That's probably longer than a graphing problem that you would see on a final exam because this would take a little bit too long, but it has all of the important features of a graphing problem.